Which of the following is not a parameter used in Gaussian mixture class for defining the model in sklearn? A. N components. B. Covariance type. C. Random state. D. Maxiter. E. All of the above. N components. The N components parameter is used to define the number of Gaussian distributions to use in a mixture model. It's essential for controlling the complexity of the model. If you want to fit the data with 3 different Gaussian distributions, you set N components 3. False. Covariance type. The covariance type parameter defines how the covariance matrix of each Gaussian component is structured. It allows choosing between different types of covariance matrices like full, tied, diag, spherical, each impacting the model's flexibility. This helps adjust the model's capacity to capture the variance and correlations in the data. False. Random state. The random state parameter controls the random number generation used for model initialization, including the starting values of the means, covariances, and weights of the Gaussian components. Setting a specific value ensures reproducibility of results, allowing you to get consistent model fits across multiple runs. False. Maxiter. The maxiter parameter limits the maximum number of iterations for the expectation maximization M algorithm. This algorithm finds the optimal parameters of the GMM, which is an iterative process. By controlling the number of iterations, you can manage the computational resources and prevent potential issues if the model is not converging. False. All of the above. All of the listed parameters are used in the Gaussian mixture class. Each parameter serves a specific purpose in defining the model, contributing to its flexibility, control over initialization, and resource management. Therefore, none of them are not a parameter of Gaussian mixture. True. E. All of the above. The Gaussian mixture model GMM is a probabilistic model that assumes the data points are generated from a mixture of Gaussian distributions. It uses a weighted sum of Gaussian distributions to represent the overall data distribution. Imagine you have data points scattered around a plane. A GMM might use 2 Gaussian distributions to represent 2 clusters in your data, where each cluster is a Gaussian distribution with its mean and covariance matrix. The N components parameter determines the number of Gaussian distributions used in the GMM. It influences the flexibility of the model. More components allow capturing more complex data structures, but too many components might lead to overfitting. The covariance type parameter specifies the structure of the covariance matrix for each Gaussian component. It allows controlling the model's flexibility in representing correlations between features. It can take values like full covariance matrix, allowing each Gaussian component to have a unique and potentially complex relationship between features. Tied. All Gaussian components share the same covariance matrix, suggesting that all clusters have the same degree of correlation and variance for their features. Diag. Only the diagonal elements of the covariance matrix are non-zero, implying that features are independent within each cluster. Spherical. The covariance matrix is a diagonal matrix with equal values across the diagonal, implying that features have equal variance within each cluster. The random state parameter controls the random number generation used for model initialization. Setting it to a specific value ensures that the model's initialization is reproducible, leading to consistent model fits across runs. This is important for comparing results and ensuring reliable performance. The maxiter parameter limits the maximum number of iterations for the expectation maximization M algorithm. The M algorithm is an iterative optimization algorithm that finds the best parameters for the GMM. By limiting the number of iterations, you can manage the computational resources and prevent the algorithm from running indefinitely if it's not converging. GMM can be used for clustering data points into groups based on their probability of belonging to different Gaussian components. Imagine you have a dataset of customer data, and you want to identify different customer segments. You can use GMM to cluster customers based on their purchasing patterns, demographics, or other relevant features. GMM can estimate the probability density function of the data. This allows you to analyze the data distribution and understand the underlying structure. For example, you can use GMM to estimate the distribution of heights of people in a population. GMM can identify data points that are unlikely to belong to any of the Gaussian components. These points can be considered as outliers or anomalies. For example, in fraud detection, you can use GMM to identify transactions that deviate significantly from the normal pattern of transactions. GMM can be used to fill in missing values in the data based on the probability distribution of A data. For example, if you have missing values in a dataset of student grades, you can use GMM to impute the missing grades based on the distribution of grades from other students.